Speed and period. The period has the insignia capital T for some historical reason. Time taken to complete one revolution. Remember, we're looking at an object in uniform circular motion, constant speed, changing velocity. The time it takes to complete one revolution is the distance divided by the speed. And so we can say that the period is equal to, the distance is, of course, the circumference of the circle divided by the speed of the object. So from that we can get T equals 2 pi r circumference over V. Of course, that can be rearranged. V equals 2 pi r on T. Here's a question for you. Actually, sorry, I'm probably going too far up there. I need to get a question. Final record has a diameter of 30 centimeters, rotates at 33.3 RPM on the turntable. Find the period of rotation. Remember from year 11 physics that the period is equal to 1 on the frequency. Remember, frequency is measured in hertz. Hertz is also 1 on the seconds. Remember that. And so I have to state here minutes because we are in minutes at this point. So which is equal to seconds. 60 seconds in 1 minute. 1.8. That sounds like a reasonable time. What formula might we use for part 2? Tangential speed, which is a V, isn't it? Or S, of a point on the rim of the record. We just looked at that. Times 0.3. I'm going to change it to meters. Oh, yes. Very good. Excellent. Thank you. Excellent. 0.15. I hope everybody can see that straight away. On 5, because we're talking in radii. And they 0.523. Somebody can confirm that. 523. This book is sometimes incorrect. I think part 1 was the toughest question. Five, two, four. Thank you. Does anybody want to have a go at 3 on the board? Centripetal acceleration, what does that look like? We know that that's A sub C, isn't it? And it's equal to what? B squared over R. Notice I'm writing my formula, the formula that I think I'm going to use for this problem before I do the problem. We know our V. We've got our units correct, meters per second. Our radius, we know that too now. 0.524 squared divided by 0.15 meters. Yes. 1.82. 3? 1.83 meters per second squared, isn't it? It's an acceleration. Don't forget those units. Have a go at this one. I'm not going to do this one right now. It says, what happens if the centripetal acceleration, if the rate of rotation is increased by 50%? Sorry, thank you. For 2.7, new acceleration. So V, yes, you've got this part right. V equals 1.5 times V. Actually, I'll write that in words. Maybe that's more clear. Times V. But does that mean that I just multiply the centripetal acceleration by 1.5 times? AC, centripetal acceleration is equal to multiplied by 1.5 squared. Remember that AC is proportional to B squared, okay? And so, which equals 4.1. Can somebody confirm that number for me? We're going to do lots of problems that talk about proportionality as we go through the course. You'll get used to these. If this is new, very new to you, then don't worry too much about it right now. We'll do lots of them, lots of practice. Forces causing centripetal acceleration. Better. If you're swinging, I'll go and cut the pictures out of the book. This is much easier. You guys should draw these. This little boy is swinging some mass on the end of a string around. And what's the force causing the centripetal acceleration? F equals FC equals MAC, remember? That centripetal force is provided by, we call it, can anybody remember? Tension. Yeah, so the vertical, yeah, I was going to mention that, but I decided not to. But what is your question? Because he's swinging it vertically. Yeah, okay. So imagine, yeah, so if he's swinging it on its way up, we have, of course, gravity is always G here. Where does the centripetal acceleration point toward? Points towards the center of the circle in all cases. And at the top of the ball's path, that centripetal acceleration is working with G, isn't it? And at the bottom of the ball's path, it's working against G. Can you see that? That's why if he's got it at a very low, if he's got it at a really high speed, it's not going to matter. You're not going to see any change in the path of the ball as it moves around this circular arc. Okay. But if he's going very slowly, you'll notice that what will happen is the ball's path may start to do these sorts of things. Cut short, and it falls. It appears to fall through the air, doesn't it? And that's G working with his centripetal force, with his centripetal acceleration. Yes, it's a good point. You will have noticed that. You need to, as we get older, when you're young like him, he might not understand that he needs to swing it at a certain speed in order to keep it in a nice circular, uniform circular motion. And that's where we get back to the video where he's trying to do the loop in the car. Frictional force. Here's a better diagram than what I drew the other day. Oh. Yeah, sometimes this program goes a bit haywire for some reason. Frictional force. Centripetal force. Provided by friction. That's assuming that this car is going around the bend, and that's flat. That's that bend is flat on the surface of the Earth. There's no banking angle whatsoever. You'll find that high-speed roads in the country are slightly banked in most cases, and that's to reduce the reliance of the friction between the tyres and the road if you bank it just slightly. And our application in this topic is banked angles when we look at the Bugatti Veyron going around the bend. And there's another, a Top Gear Australia, which I didn't think was that good, but there's one scene where they're driving a Commodore around a banked bend and he can let go of the steering wheel of the car and the car keeps turning around the bend, of course. What's providing the centripetal force in that case? The angle of the banking itself, yeah. And we're going to look at that in detail, where the force lies in that, okay? If he slows down, what happens? The car will drop towards the center. If he speeds up, he'll go out towards the outside of the track, won't he? So there's a speed that's very specific there that's necessary. Okay. Do I have the video? Yep, I've got it. Yep. We will see it. Yep, yep. How long? This one here. What's going on here? Gravitational force. I want to go to this. Here's a mass rotating around another mass. And we call that force gravity. Oh. We know that, quiet please. We know that the centripetal force is equal to the mass times the velocity squared over the radius. In this case, it's provided by gravity or gravitation. Newton's universal law of gravitation is equal to this. Have you guys seen this before? Yes. R squared. Okay, we'll leave that at that. Oh. Normal force. This one is part of our application, which you will have to learn. Quiet, please. Thank you. Centripetal force provided by, can you see what it's provided by there? Have a look at, there's the normal force. And I could draw in gravity there, couldn't I? If I wanted to. Actually, I'll do it in a different color. Do it in the color we usually use, which is, I don't know, red or pink. Gravity's going to be, if the car is in uniform circular motion and it's in fact, it's not moving up the curve, it's not moving up the bank, and it's not moving down the bank, then Fn cos theta, this component of the normal force, the vertical component of the normal force there, is exactly the same as force of gravity. So what provides the centripetal force, centripetal acceleration? Provided by the horizontal component. I'll do this in capital, normal force. See how this force here, Fn sine theta, is just the horizontal component of the normal force, is unbalanced in this case. These two vectors here are mutually perpendicular, and they are just components of this vector, this normal force vector. And so this one is the unbalanced one. That's the one that's pulling the car towards the center of the circle, providing the centripetal force, providing the centripetal acceleration. Now that's theta there and that's theta there. If you want to understand the geometry there, it's not difficult geometry, but you should go away and have a look at why that theta is equal to that theta. So that's the angle of the banked track, assuming that it's a nice straight line there. Angle of the banked track is equal to that angle in there. And we can say this. Fc is equal to the frictional force plus of the normal force. I'll just okay. F equals MA, FC equals MAC. Force of friction, this is what our text shows us. Oh, hang on. Plus F sub N sine of theta. Now this situation here is not the situation in which the car is going around the bend with the driver with his hands off of the steering wheel. This is the situation where he's got to do some steering to get around that bend. Okay? That steering there provides the friction that allows the car to go around the bend. There's some speed this V here, some speed at which he can let go of the steering wheel. And the centripetal force, it's provided by Fn sine theta only. And I think I'll show you a video. Is that where I wanted to stop? Yes.